Greetings, chemistry students. Yesterday, we looked at some orbital diagrams. We looked at how you fill this chart with electrons. Now, your assignment last night was kind of some review of other things that you learned, but we're coming back to this today because this is the foundation of what we're going to be doing today. So I do want to point out a few things that you may or may not have noticed yesterday with these orbital diagrams. For instance, if you look at a orbital diagram for hydrogen, it's just got one little arrow and a 1s sublevel. And hydrogen on the periodic table is right here. But look, below hydrogen, you have lithium on the periodic table. Lithium looks like this. Below lithium is sodium. And there's an orbital diagram for sodium. And below sodium is potassium. This is the orbital diagram for potassium. And below potassium is rubidium. And there's an orbital diagram for rubidium. So you might notice some patterns that they're all similar. They all have one electron in an s sublevel. So what we're going to do is we're going to use these orbital diagrams in order to figure out how to write what's called electron configurations, which is going to be a representation of this diagram that you're seeing without you having to actually draw these out. So electron configuration notation is an alternative to drawing those orbital diagrams. It's a little shorthand notation for it, where you list the energy level and sublevel, and then you use a superscript to represent how many electrons are in the sublevel. So for instance, if you wrote 1s1, that would mean you have one electron in the 1s sublevel, and that would be the electron configuration for hydrogen. If you had 1s2, 2s2, 2p3, that would be 2 electrons in a 1s sublevel, 2 electrons in the 2s sublevel, and 3 electrons in the 2p sublevel, and that would be nitrogen. So if we go back to the orbital diagrams and we say, let's say we're going to do an electron configuration for, let's go with phosphorus, which is element number 15 on the periodic table. It's this one right here. So for phosphorus, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 electrons. And if we're going to write the orbital diagram for that, it would look, for the electron configuration, it would look like this. It would be 1s2, because there's 2 electrons in the 1s sublevel. Then we have the 2s sublevel, and we would write a 2. And then we have our 2p sublevel, so we would go 2p, and there are 1, 2, 3, 4, 5, 6 electrons there. Then we go to 3s, and there's 2 electrons, so it's 3s2. And then we go to 3p, and there are 1, 2, 3 electrons, so 3p3. So that's how this works. So you write the energy level and sublevels, the 1s, 2s, 2p, 3s, 3p, and then you write as superscripts the number of electrons. And by the way, this order that we use is called the Aufbau sequence, where you go 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, so forth. That's called the Aufbau sequence. It's just that order that we follow. But there's a way to figure this out without using this orbital diagram at all. We can just look at the periodic table. So to do that, I'm going to make a few modifications to my periodic table. So I'm going to pretend that helium sits right here. All right, and then we've got our rows. We've got row 1, row 2, row 3, row 4, row 5, row 6, and row 7. And we're going to have a few different regions of the periodic table. So this first region right here, so this is going to be the S region. Then we're going to have this region over here. I'm just kind of roughly coloring this in. That would also include these elements down here. That's going to be the P's. Then we've got this region here in the middle. These are going to be the D's. And then, of course, that leaves the bottom. These are the F's. And there's more back here. You just can't see them right now. So the way we're going to actually do this. So essentially, this represents 1s, 2s, 3s, 4s, 5s, 6s, and 7s. Similarly with the P's, this would be 2p, 3p, 4p, 5p, and 6p. So our S's start with 1, our P's start with 2, our D's will start with 3. So this is going to be 3D. I know this is row 4, but this is 3D, 4D, 5D, and 6D. And then for the F's, our F's start with 4, so this is 4F and 5F. Something else that may not seem super obvious is where these elements down here at the bottom fit in. But this row of elements 58 through 71 slide in right between lanthanum and hafnium. And this bottom row down here, elements 90 through 103, they would slot in between actinium and rutherfordium. We pull them down to the bottom because otherwise the periodic table would be twice as wide as it is now. And so they're kind of pulled to the bottom just to make sure that there's actually, you're able to fit the periodic table on a piece of paper. Right? So given this layout, we can actually read the periodic table like you read a book, top to bottom and left to right. So if we wanted to write an electron configuration for, let's say, beryllium. Beryllium's right here. We start at the top. This is our 1s's. So we write 1s and we go 1, 2 spaces. That's the end of the 1s's. It's also the end of the first row. Then we go to the second row and we encounter our 2s's. And we go 2 spaces. So it's 1s2, 2s2. If we wanted to do an electron configuration for chlorine, we always start at the beginning. So we go 1s and we go 2 spots. Then we get to the second row, 2s, and we go 2 spots. So 2s2. Then we continue across. We have our 2 P's and we go 1, 2, 3, 4, 5, 6 elements across. So that's 2P6. Then we get to our 3 S's and we go 3S2. And then we go 3P, 1, 2, 3, 4, 5. So let's take a look at a few more. For instance, if we wanted to do iron. For iron, this is going to be too much for me to write out this way because I don't have my stylus here at the school. If we're trying to do iron, which is right there, the way you would do iron You start with your 1s's, you go 1s, 2, then you go 2s, 2, then 2p, 6, 3s, 2, 3p, 6, 4s, 2, 3d, 1, 2, 3, 4, 5, 6. That's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. And if we go back and check on our PowerPoint, if we're doing iron, which has 26 electrons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. We'd find its electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. So it's the exact same. What I'd like for you to do now is take a minute and see if you can write some electron configurations for these 7 elements. So we got helium, fluorine, argon, potassium, vanadium, zinc, and arsenic. So you may need to go back and modify. You can make notes on your periodic table and your reference tables. You can write these 2p, 3p, 4p, and the 3ds, and write them right in your reference tables. Those are yours. So make some notes in there. If you want to label the regions S, P, D, and F, go right ahead. Feel free to write all over your reference tables. And once you do that, I want you to go to these 7 elements and see if you can write electron configurations. So go on and pause the video right now and try it. All right, now that you've had a minute to try these electron configurations, you should have come up with these. Now please note with arsenic, once you reach the end of that 3D row, you go back to 4P. So getting these in order is very important. The other thing you've probably noticed is these can get very, very long. Electron configurations can be quite extensive. So you ideally want to have some type of a shorter way of doing this, because this could be incredibly tedious, use up a lot of paper, all that good stuff. So there is a shortcut that we can use, because you may notice that right here, just draw a line right down here, everything is the same for all of these electron configurations that are in the 4th row of the periodic table. So what we can do is, if we go back, when we're doing elements that are in the 4th row, if we go back to the end of the previous row, we can use these elements in the last row of in the last column of the periodic table: helium, neon, argon, krypton, xenon, and radon. We can kind of use them as bookmarks to say, we're going to start here. So instead of having to write out 1s2, 2s2, 2p6, 3s2, 3p6, we're just going to say, hey, we're starting with argon and moving forward. And so what that looks like is you take that element at the end of the previous row, you put it in square brackets, and you pick up from there. So it looks like this. So instead of writing the first part of the electron configuration, we represent that with argon in square brackets. So that saves us a lot of time. So for instance, if you wanted to write an electron configuration for francium, you could write 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, 4f14, 5d10, 6p6, 7s1, or for francium, you could, for francium, let me just change my pen color here. You could just write radon in square brackets 7s1. It's that simple. Now, there are two elements that you can't write a shortcut for. And that would be hydrogen and helium, because there's no element at the end of the previous row. Also, if I asked you to write an electron configuration for argon, let's see if I can make this work. For argon, you're not allowed to just write AR in square brackets. That is not allowed. What you can do is go back to the end of the previous row and do neon in square brackets, and then do 3s to 3p6. But you can't just write an element in square brackets and call it a day. And also, the only elements you're allowed to put in those square brackets are these elements at the end of the previous row. These elements are called the noble gases. We'll learn that in our next unit. They're called the noble gases. The key thing about this is also, instead of calling it the shortcut method, you can call that the noble gas electron configuration. So I hope that helps. There's one last thing I want to show you. It's not going to be a major focus of this class, but the F's are kind of weird because they kind of split the D's after you've started the D's. If we were going to write an electron configuration for, let's say we're going to do an electron configuration for promethium. Well, we need to go back to the end of the previous row. Just count the numbers: 61, 60, 59, 58, 57, 56, 55, 54. So xenon is at the end of the previous row. And then from xenon, we go 6s2, 5d1, 4f, 1, 2, 3, 4. Okay. So you put this 5d, you have the 1 and the 5ds, and then you go to your 4f's and go however far you go with the 4f's. If we want to do something that's after them, let's say we're doing tungsten, which is number 74. We go back to the end of the previous row, you put xenon, and then it's going to be 6s2. Then there would be the 5d1, but we're coming back to the 5d. So we're just going to hold off on writing it. Then we have the 4f14. Sorry, you can't see all of the 4f's on my periodic table because my face is down here in the way. And then we come back to the 5d's and we go 5d, and we're going to include this one. So 1, 2, 3, 4. Similarly, if we were doing lead, lead would be xenon 6s2, 4f14, 5d10, 6p2. Right. So don't forget about the F's when you cross this little barrier right here where you kind of make a detour down below. Same thing happens with the bottom row, except you start with radon in square brackets. So for instance, we want to do the most American of all the elements, americium. It would be, it's literally named for the United States of America. It would be radon in square brackets, 7s, if I can write this correctly, 7s2, 6d1, 5 F 1, 2, 3, 4, 5, 6. All right. So I hope you find that helpful.